This is my Calculus 1 course. Today we're going to learn how to determine if a value of a function is a maximum, a minimum, or neither. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we had a particular situation that we dealt with. A situation where we had a continuous function on a closed interval. So here's an example of that scenario. And we learned how to find the biggest y value and the smallest y value of the function on that interval. Today we're going to do something similar, but we're not going to have bounded functions. We're going to have continuous functions that just go off forever to the right and to the left on their corresponding graphs. And we're going to find critical numbers like we did in the previous class. And remember, critical numbers are the possible locations of maximum or minimum values. We're going to find those numbers, and then we're going to determine if those numbers lead us to a maximum value, a minimum value, or neither. Now remember that critical numbers are x values where the derivative of a function is 0 or undefined. We learned in a previous class that if you want to find a maximum or minimum value, we find where the derivative is 0, because this, for example, is a maximum value. Or this is where a maximum value is. The y value of that purple point is a maximum value of the function. And if we want to find where that maximum value occurs, and we don't have the graph, let's assume that we don't have the graph, if we find the slope of the line that is tangent to the graph at that point, we find that it's 0 because the line is horizontal. And the same is true when it comes to minimum values. The slope of the line that is tangent to the graph at that point is 0. Now remember that the slope of the tangent line, the line tangent to the graph at some point, is the derivative. The slope of the tangent line is the derivative. So the derivative is going to be 0 at these maximum and minimum values. So that's why the critical numbers, these x values, are values where the derivative is 0. Now, where the derivative is undefined, those are also going to be critical numbers. So, for example, there would be a critical number here. The x value that gets you to this blue point down here, that's a critical number because that's where the derivative is undefined. The derivative is undefined there because if you try to find a line that's tangent to the graph at that point, well, there's all kinds of different lines. There's an infinite number of lines because the lines just kind of teeter on that point. So in this class, we're going to find the critical numbers, and then we're going to test the function at those critical numbers to determine if there's a maximum value of the function, a minimum value, or neither a maximum nor a minimum value at each critical number. Okay. Now, the situation where you have neither a max or a min is a situation where you have a function that looks like this if you were to graph it. The line that is tangent to the graph at this point is horizontal, which means that the slope of the line is 0. That means that the derivative of the function is 0, because the derivative of the function is the slope of that tangent line. So the x value at that point would be a critical number because the derivative is 0. But in this situation, you can see that this point, its y value, is not a maximum or minimum value because it's not the top of a hill and it's not the bottom of a valley. It's just kind of a part of a shelf. So that's the situation today. We're going to test functions at critical values to see if we have maximum or minimum values. And the test that we're going to use is called the first derivative test. So I want you to get a picture of this. And you might wonder, well, why are we calling it the first derivative test? Well, we're going to learn today that there's actually something called the second derivative and the third derivative. We haven't learned that yet, but we're going to learn that as we go along here. And I'm not going to read all this, but I'm going to demonstrate right now the principle behind this first derivative test. Once you understand the principle, you're going to find it's really not a difficult concept at all. So I guess we can use this graph over here. So let's say that we find our critical numbers, that the numbers that make the derivative 0. So that would be at the bottom of the valley, at the top of the hill, and where we have a kink in the graph, or a sharp turn. So we know that this point here, its y value is a maximum value. But let's say that we didn't have the graph. Let's say that we just found the critical numbers. And without seeing this graph, we want to test to see if this critical number here is the location of a maximum or a minimum, or neither. Again, we're going to use what's called the first derivative test. So the way the test works is you find a point on the graph that's to the left of that blue point, and you find the slope of the line that's tangent to the graph at that point. Now remember, the slope is the derivative of the function. And the derivative, the slope of the orange line is going to be positive because the line is going up, right? Then you're going to find a point to the right of that blue point, and you're going to find the slope of the line that's tangent to the graph at that point. And the slope of the purple line, which again is the derivative, the slope of the tangent line is the derivative. The slope of the purple line is going to be negative because the line is going down from left to right. So notice that when we crossed this blue point, when we started at the left of the blue point and then crossed over to the purple point, as the tangent line changed, it actually went from a positive slope to a negative slope. So that proves that the blue point, its y value is a maximum value. So just to be absolutely clear what we're talking about here, again, let me show you. So look at this pink point here. The slope of the line tangent to the graph at that point is positive because it's going up from left to right. But look what happens as you bring the point closer. The line that's tangent to the graph at that point kind of starts to level off. So the slope of that pink line is still positive, but it's not as big of a positive number. And then as you get to the top of the hill again, the line that's tangent to the graph at that point actually becomes horizontal. Its slope is 0. But then, as the point goes farther to the right, then you find the slope of the line that's tangent to the graph at that point, and now the slope is negative. So again, the sign of the derivative changes from positive to negative. So that proves that this point here contains a maximum value. The y value of that point is a maximum value. Remember, the x values of a function are considered to be the locations of the values of the function, but the y values are the actual values of the function. So that's called the first derivative test. We're just going to check the sign of the derivative to the left of the point and the sign of the derivative to the right of the point, and if the sign changes from positive to negative, that means you have a maximum value. And this is assuming that we're dealing with a continuous function. If you don't have a continuous function, this test doesn't work. It doesn't necessarily work. Well, now let's say that we're dealing with a minimum value. The test works the same way, except now when you're to the left of that point, the slope of the line tangent to that orange point is going to be negative. But as you cross over to the purple point, now the slope of the line tangent to the graph is positive. So remember, the slope is the derivative. So if the derivative changes sign from negative to positive, as you cross over the location of this possible max or min, then you have a minimum value. And the same is true when you have a critical number that makes the derivative undefined. So that would be this blue point here. That's the possible maximum or minimum value. And this x value should be a little closer there. So if you choose a point to the left of that blue point and find the slope of the tangent line, the slope is obviously negative because the line is going down from left to right. But if you choose a point to the right of that blue point and find the slope of the line tangent to the graph, the slope of the purple line is obviously positive, right? Because it's going up from left to right. So because the slope of the tangent line, that is the derivative, changes from negative to positive, that blue point contains a minimum value of the function. The y value of that point is a minimum value of the function. So that's how this works. So I want you to get a picture of this information here. We're not going to read all this because we kind of just explained it. And let's do some practice problems. Now again, in this situation that we just explained, we had a graph, but this test is used when you don't have the graph in front of you. All right. So these problems say, without graphing, without using your graphing calculator, find the x values where the local maxima and minima of each function occur. Use the first derivative test to verify that the x values that you found are indeed the locations of extrema, and to distinguish between maxima and minima. So we're going to find the x values where maxima and minima occur, and we're going to show if the critical numbers led us to a maximum or a minimum value. So we need to first find the critical numbers. Remember, if you're looking for fish, you need to find where there's water. Now, if you find where there's some water, that doesn't mean that it's proof that there's fish there. But if there are going to be fish, you have to find where the water is. Well, the water is the critical numbers. If you find a critical number, it doesn't prove that there's a maximum or minimum value there. But if there is a maximum or minimum value there, it's going to be at the critical numbers. So we first have to find the critical numbers. But again, what are critical numbers? Critical numbers are where the derivative is equal to 0 or undefined. So first we have to find the derivative. So that's the derivative. That's what we've been learning to do, is find the derivative in the last 5, 6, 7, 8 weeks. So now, remember, critical numbers are x values that make the derivative 0. So I'm going to set the derivative equal to 0 and then find those critical numbers. So in order to do that, I'm going to factor a GCF. And now we have the x values that make the derivative equal to 0. So these red values here, those are critical numbers. So again, critical numbers are the possible locations of maximum and minimum values. Then I'm going to use what we call the first derivative test. And the test, as the name implies, uses the derivative to help us determine if there's a maximum or minimum value. So I'm going to rewrite the derivative function. This is not the original function This is the derivative of the original function. The original function that we're dealing with is this yellow function here, right? Well, when we're doing the test, we're using the derivative of that. So I'm going to draw the number line. And remember, these are the critical numbers. That's where the water is, but we don't know that if there's fish. So we're going to mark those x values on the number line. And the way that the first derivative test works is we're going to test the derivative, or we're going to test the derivative function in that region. We're going to test the derivative in this region, and we're going to test the derivative in this region. And what we're looking for is the sign of the derivative. Remember, if you have a maximum value, then the slope of the tangent line goes from positive to negative as you cross the critical number. So we're going to plug in some value here into the derivative and see what the sign is. Is it going to be a positive number or a negative number? Then we're going to plug in some value in this region and determine if the derivative is a positive or a negative number. And same thing here, and that's going to tell us if these critical numbers are the locations of maxes or mins. So let's do this. So I'm going to test this region. So I can plug in any number that I want in that region. So I'm going to plug in -1. Now you can plug in -2 or -3 or -100. It doesn't make any difference. Just try to plug in the easiest number that you can find. And we get 15. Now 15 is a positive number. That's what we're looking for. We're looking for the sign. We don't really care what the number itself is. We just want to know what the sign is. So that region is a region where the derivative is positive. So I'm going to put a plus sign up there. Now we're going to test the yellow region. I'm going to plug in 1. Why 1? Because 1 is in this region. 1 is between 0 and 4. And I get -9. So that is a negative number. So the sign of the derivative is negative. So I'm going to go up here and write a negative symbol there. So that is the yellow region. Okay, and then I'm going to test the green region by plugging in 5. Why am I plugging in 5? Well, because 5 is in this region here. So we have 3 times, and I got to make sure to write my prime symbol, 3 times 5 squared minus 12 times 5, and that is 15. So 15 is a positive number, so I'm going to go up here and write a positive symbol. Okay, so now we've done all the busy work. We're done with the busy work and we're ready to actually make our conclusions. This sign chart tells us if x equals 0 is the location of a maximum or minimum or neither, and it also tells us whether or not this location here where x equals 4 is the location of a maximum or minimum value or neither. Maximum or minimum value of the original function. So again, let me show you how it does that. What this sign chart tells me is that the graph looks something like this. Now my graph is not perfect because I'm not, taking the time to actually calculate values. But what I know is that there's a maximum value where x equals 0. That's this orange place here. And I also know that there's a maximum value, or excuse me, there's a minimum value where x equals 4. That's this pink area down here. And how does it do that? How does this sign chart tell me where the maximum and minimum values are? Well, again, let's explain the general concept. It's so important for you to understand this. It's not a difficult concept, but if you understand the basics of it, you can see this is really an easy concept. It's all based on the idea of a tangent line. The derivative function is the slope of the line that is tangent to the graph at some x value, whatever x value you plug in. So if we're dealing with x equals 0, that blue point, what we do is we plug in some value, some x value into the derivative function. So we're choosing a point to the left, and in this case it would be x equals -1. So we're plugging in -1 in this blue region into the derivative function, and we're figuring out what the sign of the derivative is. The sign is positive because the slope of the line tangent to the graph is positive. The line is going up. So that's the blue region here. But when you look at a point to the right of that that blue point, let's say this red point, that would be the yellow region, and you find the slope of the line that's tangent to that red point, you find that the slope of the line that's tangent to that red point is negative because the line is going down. Again, the slope of those tangent lines is the derivative. So the slope of the red line is now going to be negative. That's when we plugged in +1. So this red x value might be +1. That's where we plugged in +1 over here, and we got a negative number, -9. So that told us that the slope is changing to negative. So that tells us that the blue point, its y value is a maximum value of the function. It's the top of a hill. And the same logic is true for the bottom of a valley. The sign of the derivative changes from negative to positive, which means that we have the bottom of a valley. So again, these are very, very easy ideas. So what's the conclusion? The conclusion is x equals 0 is the location of a maximum value. So we located where the value is, and we also identified it as a maximum value. That's the point of these problems. We found the location of another extrema. X equals 4 is the location of another extrema, and we identified it as a minimum value of the function. Now, these may or may not be absolute maximum values or absolute minimum values. We don't really care. But regardless of whether or not they're absolute or just local, remember, every absolute value is also a local value, as long as it's not an endpoint of an interval. But again, we're not dealing with closed intervals. We're dealing with intervals where there's no bounds. We're not dealing with any kind of finite intervals. There are no bounds. So let's try another problem. Let's remind ourselves what we're trying to do here. We're trying to find the locations of maximum and minimum values of functions, and we're trying to identify these values, these extrema, as either maxes or mins. Are they maximums or minimums? So if we want to find fish, where do we look? Where we look where there's water. If we want to find maximum and minimum values, we look for the critical numbers. That's the water. We don't know if a critical number is the location of a maximum or minimum, but if there are maximum or minimum values, they're going to be at the critical numbers, so we have to find the critical numbers. But what are the critical numbers? Well, the critical numbers are where the derivative of the function is 0 or undefined. But in order to figure that out, we need to first find the derivative. And it's going to be a lot easier to find the derivative if we change to exponential form. And so now let's find the derivative. Now remember, the power rule tells us that 1/3 comes down and it multiplies into the 6, but I'm going to, you don't have to show that, but I'm going to go ahead and show that. And then we end up with 2x to the negative 2/3 power minus 2. So we've been doing this for many, many weeks now. That's just basic derivative stuff. So now we have a negative fraction exponent. We have to bring the expression down so it becomes a positive 2/3, but we also have to get rid of the fraction exponent and change it to cube root of x squared. And we can't forget to well, that's fine. Okay, so we have the derivative. But remember, in the previous class, we learned that when you're trying to find critical numbers, it's best to combine the terms of a derivative function into one expression. And it just makes the expression more presentable and easier to analyze when finding critical numbers. So I'm going to change 2 to 2 over 1, and then I'm going to multiply both sides of that resulting fraction, and that's going to give us a common denominator. And you don't have to show all this because it's kind of tedious to show the algebra, but we're going to combine to one expression. And again, this is an expression that is very presentable when it comes to discovering the critical numbers. If you don't combine all the terms into one expression, then it makes it easy to miss some of the critical numbers. So now we have the derivative expression, and remember, the critical numbers are x values that make the derivative undefined or 0. So if the derivative is 0, then that means that the numerator of this fraction is going to be 0. But if the derivative is undefined, that means the denominator of the fraction is going to be 0. Now here you can cube both sides of the equation and square root both sides of the equation, but it's obvious that x has to be 0 in order to make that work. You don't have to show all that. Over here we're going to add 2 cube root of x squared to both sides, and we end up with this equation. Then you're going to divide both sides by 2. Again, you don't have to show this. Then you're going to cube both sides of the equation and then square root both sides of the equation. And when you do that, you end up with x is equal to plus or minus 1. You can see that if you plug in 1 or negative 1, the equation works. So we found the critical numbers of the function. So now we're going to test the function at the critical numbers. Now at this point, notice that we have a lot of different versions of the derivative equation. We have the yellow version, the blue version, we have the orange version. If we're going to test the function using the first derivative test, we have to use the derivative function. Remember, that's how the first derivative test works. But which equation do we use? Well, we use the easiest one to use. The easiest one is going to be the blue one. So I'm going to copy that blue equation and paste it, just so we don't have to constantly look down. The reason that we're not using the version that we came up with here, because you're probably thinking, well, we combined everything to one expression. I thought we were going to use this version. This version is good to find the critical numbers, but it's not the best version to find the sign of the derivative. That's what we're going to do next, because this version is much easier to use for that. So you can use any form of the derivative function, but you want to find the easiest form to use when doing calculations. So now we're going to write -1, 0, and +1 on a number line, because those are our critical numbers that we found. So we found those critical numbers by setting the derivative equal to 0. We found where the derivative is 0 and undefined. So what we're going to do is we're going to test the blue region, the yellow region, the green region, and the purple region to see what the sign of the derivative is, and that's going to tell us if there's a maximum or minimum value at x equals -1, a maximum or minimum value at x equals 0, or a maximum or minimum value at x equals 1. Or we could have the situation where there's neither a maximum or minimum value. Again, these critical numbers are the possible locations of extrema. Now I'm going to try to find a number that is I'm going to try to find a number that makes it to where I don't have to use my calculator. Now, in this situation, you're most likely going to have to use your calculator. So you can enter this into your calculator. If you're using a TI-84 Plus, you can use the green alpha button at the upper left, and then after pushing the green alpha button, push the y equals button at the upper left, the stat plot F1 button. Then push enter, and it gives you a fraction template. Now you can push the down arrow key, and then you can push the math button at the left, the kind of middle upper left. Then go down to number 5, and that puts a root symbol. So you can play with your calculator and figure out how to do that. But I'm going to plug in a value that makes it to where I don't have to use my calculator. I'm going to plug in -8. -8 is to the left of -1, so it's in the blue region. So I'm testing the blue region again. And the reason that I plugged in -8 is because when we square that, we get 64. But 64 is kind of just a rare case where it's a perfect cube, so I don't have to use my calculator. So the cube root of 64 is actually 4. And so then we have 1/2 minus 2, which is -1.5. So that leads us to a negative value for the derivative. So I'm going to go up here and write a negative symbol. Now I'm going to test the yellow region. So I'm going to try -1/8. Now again, you might have to use your calculator. It's not going to be exactly obvious that -1/8 is going to be a number that allows us to avoid the calculator. So if you have to use your calculator, don't be ashamed of that. Finding that weird value, -1/8, is not going to be something that's easy. So now let's check this yellow region. Again, we're plugging these numbers into the derivative. So if we square -1/8, we get 1/64. And 1 over 60, the cube root of 1 over 64 is 1/4. So we have 2 over 1/4 minus 2. And we get 8 minus 2, which is 6. And so we have a positive number. Now this here is a perfect example of the type of math that you're expected to know when you enter a calculus course. In my pre-calculus review part of this course, at the very beginning of the course, we talked about this type of thing. This is the type of math that you're going to be expected to know, but a lot of students don't know how to simplify something like that because they just were not taught in school. So again, you're going to be expected to just be able to figure that out. It's 2 divided by 1/4, which is the same thing as 2 times 4, because you flip the divisor and multiply. Remember, a division, a fraction line is interpreted as a division operation. So now we're going to go up here and write a positive symbol. And then we're going to test the green region. And of course we're going to plug in a number in the green region. And I'm not going to actually do this. Well, we get 8 minus, looks like we get 8 minus 2 again. So the green region produced a positive number. So notice that's kind of interesting. We actually didn't have a sign change for the derivative. The derivative is that orange expression up there. And we're checking the sign of the orange expression. So we have one more region to check, that purple region. So let's plug in, I'm going to plug in 8, positive 8, just because it's an easy number to deal with. So we have 2 over the cube root of 8 squared minus 2, and that leads us to negative 1.5. So we tested the purple region and we got a negative number. So I'm going to go up here and write a negative there. And okay, so we get a negative number, and so now the situation that we have is this. That's what the function would look like if we graphed it, something like that. So we have the sign of the derivative changing from negative to positive. That's this minimum value here. And we have the sign of the derivative not changing across this critical value here. And so if this critical value doesn't lead to a maximum or minimum value, then why is it a critical value? Well, it's a critical value because at x equals 0, the derivative is not defined. And the reason it's not defined is because, again, the derivative is the slope of the line that's tangent to the graph at that point. But the tangent line, as you can see, is vertical. So a vertical tangent line doesn't have a slope. There is no slope. So the derivative is undefined when x is equal to 0, because the the slope of the tangent line doesn't exist. And then when the derivative changes from positive to negative, that's this situation here, again, which is a maximum value. So we have a local maximum at x equals 1, and we have a local minimum at x equals -1, and x equals 0 is not a maximum, it's not the location of a maximum or minimum. So again, if the sign of the derivative changes, then you have a maximum or a minimum value. That's these situations here. But if the sign of the derivative does not change, then you don't have a maximum or a minimum value. And again, this is assuming that we're talking about a continuous function. Now it's important to understand that the derivative function is not continuous when x equals 0, but we're not talking about the derivative function, we're talking about the original function being continuous. Okay, so let's try one more problem before you try one on your own. So we're going to find the possible locations where there's a maximum or a minimum value of a function, and then we're going to determine whether or not a location is a maximum or a minimum. So again, if you're looking for fish, you first have to find water. The water is the critical numbers. So we're going to find the critical numbers, but we can't do that unless we first find the derivative of the function. So now we have the derivative, and now we're going to set the derivative equal to 0, because remember, critical numbers are x values that make the derivative 0. Whoops, there should be an x right there. Sorry about that. So we're setting the derivative equal to 0, and we're going to find the x values that make it 0. There are no x values that make this function undefined. So I factored out a GCF, and now we're going to factor that quadratic expression. Looks like it's going to be -4 and -5. So now we have our critical numbers, the numbers that make the derivative 0. So those are the critical numbers, the possible locations where maximum or minimum values happen for functions. So now we're going to test those locations to see if there's a maxima or a maximum or a minimum value. So I'm going to copy the derivative formula and bring it down just so we don't have to constantly scroll back up. And I'm going to make a number line, and I'm going to write the locations of the or I'm going to write the critical numbers on the number line. Then I'm going to check this region, this region, this region, and this region. So we're going to check the sign of the derivative. So I'm going to plug in -1. So we get negative 20, let's see, negative 200, looks like that's going to be negative 600, which is obviously a negative number. So we found that the derivative is negative in that region. So now I'm going to test the yellow region, and let's try plugging in 1. And looks like we're going to get 240. So that's a positive number, so we can then write a positive symbol up here. Okay, and then we're going to check the green region, so I'm going to try to plug in 4.5, I guess. Now, this is where it's probably best to use your calculator, obviously, because things get pretty messy. So I'm entering this into my calculator, and I got negative 22.5, but I'm going to enter that in or show the substitution. So that's negative 22.5. So the derivative is negative, so I'm going to draw a negative symbol on that green portion. And finally, we just need to check the purple. So I'm going to choose 6. Now again, 6 is a very big number, so you may want to use your calculator for this. That's completely fine. So let's enter that into our calculators, and I got 240. So that is a positive number, and so this region is positive up here. So we don't have to draw the graph, but if we did draw the graph, it might look something like this. So we have a minimum value at x equals 0 because the derivative sign is changing from negative to positive, so we might have a minimum there, and then we have a maximum at x equals 4, and then another minimum at x equals 5. So our graph might look something like that. So we have 0 is again a minimum, and then 4 is a maximum because we're changing from positive to negative, and x equals 5 is another minimum because we're changing the sign of the derivative from negative to positive. So that's kind of the situation that we're dealing with. So there's a local maximum at x equals 4. If you look at those signs, and there's a local minimum at x equals 0, and also when x equals 5. And probably should say x equals 5 just to eliminate ambiguity. So now it's time for you to try. I want you to take a picture of this information, and you can get a picture of problem number 1. and get a picture of this problem here for you to use as a reference, and also get a picture, well, you can just keep number 3 in the window. So I want you to try number 4. Now please be aware that for number 4 you're going to have to use the -1 rule. You're going to have to factor out a -1 from the derivative expression, and you're also going to have to factor the difference of two squares. So remember, if you have something like x to the 4th minus 16, you can factor that to x squared minus 4 times x squared plus 4. We haven't done that for a while in my curriculum, where we had 4th powers, but that's the same as the difference of two squares, because you have x squared squared minus 4 squared. It's the difference of two squares. And be aware that you can continue to factor to x minus 2 and x plus 2, and the x squared plus 4 doesn't really factor, because it's the sum of two squares. Now your problem is not going to be exactly the same as that, but it's going to be similar. Also, you're going to get something like negative x to the 4th plus 16. You can't really factor that. You have to factor out a -1 first. So these are the things that you're just going to be expected to know how to do in the calculus curriculum. Now if you forgot how to do it, that's okay. We'll do it together, but attempt this. So what we're doing is finding the possible locations where maximum and minimum values occur, and then we're identifying if we have a maximum or a minimum. So try number 4. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. So go ahead and take a picture of these problems here, and we're going to go on to another one. So go ahead and try number 5. We need to find the locations of possible maximum and minimum values, and then identify whether or not identify whether or not the function has a maximum or minimum at those locations. So go ahead and attempt number 5. When you come back, we'll do it together. All right, we're back. There's no maximum value of the function, and there's no minimum value of the function. So what would this look like? Well, we're not really sure exactly what the graph would look like, but at x equals -3, you have something like this. So it's going to be kind of like a shelf. So it levels off here, and the tangent line at that point on the shelf is actually horizontal, which means the derivative is 0. So that's why setting the derivative equal to 0 led us to that point. But you can see that the function doesn't have a maximum value here or a minimum value. It's just a part of, it's just landing on a shelf here. Okay, so that was kind of a tricky one, because there was really no answer other than there is no local maximum or local minimum. So sorry if that was kind of a trick question there. This is the third situation that we just dealt with. If the derivative of the function does not change sign at x equals a, then the function does not have a maximum or minimum value at x equals a. We dealt with that situation here on problem number 2 also. Okay, so go ahead and try number 6. Again, we're looking for the locations, the possible locations of maximum and minimum values of the function. And we want to identify them and figure out which location produces a max and which location produces a minimum. So try number 6. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. And I guess we could rectangle these answers that we did on the previous problem, even though they're not really numbers. Okay, so if you got those right, excellent. So now we're going to some problems that are a little bit more difficult. Remember when we learned how to do all those differentiation formulas? Well, on this problem, finding the derivative is going to be much more challenging, because we have the product of a blue thing times a green thing. So if you want to find the derivative, you have to use the product rule. So first thing we're going to do is change to exponential notation, because that just makes things easier. And then we're going to find the derivative. But remember, we have to use the product rule, so we have to find the derivative. In fact, I'm going to go ahead and paste the rule up here. Maybe I'll change that color just so you know it's not part of the math. So we need to find the derivative. And by the way, there's a number of ways to do this, but the easiest way is to make 2x the first expression. Make that f of x. So maybe I'll write that up here. Okay, so we find the derivative of 2x, and then we multiply that by whatever the second expression is in the product, and then we add 2x times the derivative of whatever the second expression in the product is. Okay, so now, and by the way, I want to make something very clear. You don't have to show this stuff. You don't have to do this pink intermediate step. Very, very important to understand. You really should be able to do this without the d over dx, all that notation. So the derivative of 2x is 2, and that's still multiplied by x squared minus 9 over to the 1/5 power. And the derivative of this, well, you have to use the chain rule, because we have a function inside another function. And this is the part of the course where students really start to get tired of that chain rule. They don't like the chain rule, but whether you like it or not, you're going to have to use the chain rule thousands and thousands of times, so just get used to it. So we found the derivative of the outside function. That's step number 1. We kept the inside function, we didn't do anything with it. But now we're going to multiply by the derivative of the inside function, which is 2x. So I'm going to show that work. Multiplying by the derivative of x squared minus 9. The derivative of x squared minus 9 is 2x. I'm going to use a lighter color there. Okay, so you can see that this is kind of involved, having to use the product rule. So we have 2x, or 2 over 5x times x squared minus 9 to the negative 4/5 power the derivative of x squared minus 9 is 2x. Okay, so you don't have to show every single one of these steps. I'm just going slow so you can see what's happening. And then we have 4 over 5 x squared times x squared. Well, I guess we can just go ahead and write that as one fraction. So 4x squared over 5 times the fifth root of x squared minus 9 to the fourth power. So I know that that's a lot to deal with, but again, this is calculus. So I'm just warning you that students are going to be expected to know how to do this algebra. And if you're having a little trouble with the algebra, then join the club of the millions of students that take calculus and they are a little rusty with the algebra. But you need to get on board with the algebra really, really quickly, because algebra can get really out of hand in calculus courses. And you have to really take it seriously, because the algebra is not going to get any easier. I'm not trying to scare you. I'm just saying, I'm just letting you know that this is the way calculus is. So let's double check everything, make sure we did everything correctly. And everything looks right. And now that I think about it, it's probably best to write the x squared minus 9 as to the 4/5 power. We'll just keep it like that for now. Okay, so now we need to get a common denominator. Remember what I said, when you're trying to find critical numbers, it's best to combine terms into one expression. So I'm going to copy this. And I'm going to write this term as that expression over 1. And then I'm going to multiply both sides of the fraction by this expression down here to get a common denominator, so we can combine everything into one term. My computer's going kind of slow. Sorry about that. Things would be a lot faster if computers ran faster, but that's just the way of the world. Okay, so we're going to get a common denominator here, and something kind of convenient is going to happen when you multiply. Well, first of all, when you multiply 5 and 2, that just becomes obviously 10. But notice the base. I want you to notice x squared minus 9, x squared minus 9, they have the same base. So what that means is that you can combine those terms into one. It's like x to the 1/5 times x to the 4/5. You can do that. You can add those together. So we're using exponent rule number 1, where you just simply add the exponents and you get 1. 1/5 plus 4/5 is 1. So we just get x to the 1 power. So this is going to be x squared minus 9 to the 1/5 plus 4/5. So I'm going to write the intermediate step just to make sure that you understand exactly what's happening. I'm going to copy this again. And in the denominator we have this expression. So let me make some more room. So we're going to continue our work up here, and so I'm going to copy this whole thing, and when you add these yellow exponents here, again we get 1, so that's just going to turn into 1. And now we can add these fractions together. Because we have a common denominator. We can also multiply these, so we get 10x squared minus 90 plus 4x squared all over 5 times x squared minus 9 to the 4/5 power. So now we have one expression, but we can still simplify this a little bit. So we have 14x squared minus 90 all over 5 times the 5th root. Let's change it into a root now, because remember, we can't really understand fraction powers. We need to switch to a root so we can really understand what's going on. So now with this expression we can figure out what the critical numbers are. So a big part of this problem is just finding the critical numbers, and you might be wondering, is this really necessary? Are they going to make us do this in calculus? And the answer is yes, they are going to make you do this in calculus. The algebra gets pretty intense. So I'm sorry about that, but that's why calculus is considered to be so challenging, especially the first course in calculus. So we're going to set the numerator equal to 0, because that means that the derivative is 0, and we'll end up with x is equal to plus or minus 90 over 14, which is 45 over 7, plus or minus the square root of 45 over 7. So add 90 to both sides and divide both sides by 14, and square root both sides, and don't forget to write your plus or minus symbol. Now if the denominator is 0, if the denominator of the derivative is 0, then that's going to give us a critical number too. We have 2 critical numbers here. So there's a lot of stuff that we have to do to solve this. We have to divide both sides by 5, raise both sides to the 5th power, then 4th root both sides of the equation. I mean, it just goes on and on and on. And maybe I should show some of that just so you can see. So we're going to divide both sides by 5. Then we're going to raise both sides to the 5th power. You don't have to show all this if you don't want to. Then we're going to square root both sides, or excuse me, we're going to 4th root both sides. And whenever you root something where the index is even, you have to write plus or minus, but it doesn't really matter here because plus or minus 0 is only 0. It's not going to have more than one solution. Okay, and then we're going to solve, and we get x is equal to plus or minus 3. So there's actually 4 critical numbers. So now we're going to use the first derivative test. So let's find the easiest form of the derivative, because we're going to have to test the derivative. We're going to have to test the sign of the derivative, and I guess this form up here is probably the easiest form. Now again, I know that this algebra is very tedious. There's a lot of algebra going on here, but again, I can't save you from that in calculus there's just going to be a lot of algebra. I can't always protect you from every difficult thing in the curriculum. It's going to get rough sometimes. So we're going to test the derivative, but we need to write our sign chart first. So we have -3 and +3. And the square root of 45 divided by 7, that's going to be roughly 2.5354. So it looks like we have other critical numbers here, -2.535 and +2.535. Now this is going to be difficult to check all these regions. So I would recommend entering this into your calculator, into the graphing part of your calculator. If you're using a TI-84 Plus, the Y equals button at the upper left, clear out everything and push the green alpha button, and then the Y equals button, and then press enter, and it should give you a fraction template. And then push the math button and go down to number 5, and it should give you an nth root. It's still difficult to plug it into the calculator. It's going to take some time, but you don't want to have to do all these calculations manually. So we need to find f prime of -4, the blue region, and I'm not going to plug all this in. I'll just maybe do it one time so you can see what exactly we're doing. But we're going to find the value of the derivative in that blue region. And so I have the equation entered into my calculator. So I'm going to push the blue second button and then the calculate button, the trace button at F4 at the upper right. I'm going to press enter, and you want to make sure that you can see the graph. If your window's not right, it's not going to give you the answer. So let's enter -4 and then press enter, and we get 5.65 roughly. So we don't really care about the number, we just want to know what the sign of the number is. So that's positive, so put a plus sign there. And again, it's going to take too long to enter all this stuff in, so we're gonna do it on the calculator. The blue second button and then the trace calculate button. Press enter, and then it should say x equals, and we'll enter -2.6. Check it, and we get 0.486. We'll just round up to 8 approximately. So that is a positive value. Notice that the sign didn't change. That's what's interesting about this graph. The sign didn't change there. So now we're going to check the green region, and whoops, I forgot to write my prime symbol there. That's prime. Check the green region, we can check 0. And for 0, it looks like we are going to need the calculator. It's still not an easy calculation. So the blue second button and then the trace button and then enter. And then enter 0 and enter, and we get approximately -3.1037. So that is a negative number. And so then we're going to plug in positive 2.6 in the purple region. So if we plug in positive 2.6, we'll get approximately 0.4868. So it's a positive number. So our derivative is changing back to positive. And that was the purple region. Now we're going to check the pink. And we can try positive 4. Again, it's very handy to have the calculator to help us with this. So then we get 5.65 approximately, which is a positive number. So how do we interpret this? What's going on? Well, I'm going to show you the graph. You're not really supposed to graph, but I'm going to show you what's happening with this graph. The graph is going, it kind of looks like this. We have a vertical tangent line and a maximum value and a minimum value and a vertical tangent line. I didn't really draw that well, but so it looks something like that. So notice that in these pink regions we have a vertical tangent line. The graph is going straight up, and so that corresponds to these. That corresponds to when x is -3, because the derivative is not even defined when x equals -3. So that's why it's a vertical tangent line. And then these regions here are the maxes and the mins. So we have a maximum value here and we have a minimum value here because the derivative changes sign. So again, look at, we're not really supposed to graph, but look at the sign changes when you change from positive to negative. Again, this is the derivative we're talking about. When you change from positive to negative, it's a maximum value. So there's a local maximum at x is equal to approximately -2.535. And there is there's a local minimum at positive 2.535. So there you go. So again, because there's no sign change, here and here, that means that there's no maximum or minimum value. So now it's time for you to try a problem like that. Go ahead and get a picture of problem number 7 and a picture of this here, and I want you to go ahead and try number 8. And I'm going to write the product rule up there for you because you're going to need the product rule on this problem. So go ahead and try number 8. When you come back, we'll do it together. Okay, we're back. So if you got that answer, excellent. You can look back over this work and check it if you want. There's the answer. Now, again, you may have had some trouble with these signs. You see this blue negative symbol up there? That gets distributed and changes the sign of the numerator, so a lot of students have trouble with that. So if you didn't see that sign, pretty much a guarantee that students are going to have trouble with that. Some students may not have seen the sign, the negative symbol. Some students may have seen it, but they only changed one sign up here when they got down to this step. So remember, calculus is very algebra intensive. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, screenshot number 2, and screenshot number 3, and number 4, and 5, 6, 7, and 8. But don't go before you get the homework. Remember, the homework is not optional. Here's screenshot number 1 of the homework, and screenshot number 2, and number 3, and number 4, and number 5. But don't go before you get the answers. It's not enough just to attempt the homework. It must be done correctly and neatly. So here are the answers. So be sure to check all of your answers, and if you get a problem wrong, go back and fix it. Do not finish the homework until you have all these answers. Make sure that you do the problem correctly. So get that homework done, and I'll look forward to seeing you in the next class.